Hi everyone, thanks so much for coming. Thanks to the organisers. It's been a really wonderful meeting so far. I've really enjoyed it. It's a really beautiful setting. So I'm going to talk about a project I've been working on for some time with Sean Gribb. I'll proceed as follows, and so that the sections get longer as I go on. So if you're worried I'm going through things too quickly and it'll be over too soon, don't worry, the last few sections I'm not bored. So I'll start with some remarks about time and change, the kind of broader philosophical notions that I'm quite interested in. I'll then talk about a kind of quite technical and very important and rich question to what we mean by singularity resolution in a prospective theory of common cosmology. And then I'll kind of launch into mine and Sean's approach, which is based upon something we call relational quantization. And I'll give you some details about how this approach can be applied to a mini superspace model, very simple mini superspace model, leading finally to the last section actually showing some results that give us a particular form of bouncing cosmology. So time and change. It starts almost at the beginning with Leibniz, and in the correspondence he says the following. Instants considered without the things are nothing at all. They consist only in the successive order of things. And this notion of successive order is the thing that I want to really draw upon. Secondly, mark. It's utterly beyond our power to measure the change of things by time. Quite the contrary, time is an abstraction at which we arrive by means of the change of things, made because we are not restricted to one definite measure, all being interconnected.
Okay,
and here, the two things I want to draw upon is this idea of abstracting measure of duration from change, on the one hand, and secondly on the idea of the measures that we abstract being interconnected. And at least to my final kind of influence, philosophical forebear in a sense from what me and Sean want to do, which is Julian Barber, which very succinctly says the universe is its own clock. And so I can talk at probably far too greater length about how the ideas of Leibniz, Barber and Mach have influenced Schrödinger and how we see them as at least giving some philosophical platform for what we want to say. But I won't go too much detail about that. I'm happy to give a bit more exegesis Q&A if people want. Rather, let's think about things in a kind of quite simple grid. So if we think about three different notions of time, and we distinguish between them in terms of whether or not time in each notion possesses one of two properties. So one property is duration in some absolute sense, one property is succession. And I mean very precise things by these. I actually, really, what I mean by duration is a temporal metric, and what I mean by succession is the parameterization of non-homology increasing. I do not mean anything like a privileged arrow of time or a notion of becoming or anything like that. I mean a very sparse structure where simply time can't loop back on itself. That's what the monotonicity requirement is, and that's what I mean by succession, ambiguity. So let's think about three notions of time. The simplest and most natural one in a sense is where we have both duration and succession. And I think it's reasonable to see Newtonian time as a model of absolute time in this sense, the time of Newton's principle. Then the view that I'm interested in defending and developing is relational, what we call relational time, where we don't have absolute duration, but we do have succession. And I'm calling it relational time because I see Leibniz, Mach as the kind of founders, or in various senses of relationism, and as I think the quote suggested, although they might not be in favour of absolute notions of duration, this succession structure does seem to be implicit in their work. And certainly when it comes to classical physics, it's also implicit in, or even explicit in the work of Julian Barber. I would say that when it comes to quantum physics, he vehemently disagrees with us. So I'm not signing him up to that aspect of our proposal at all. So the final option is probably the one that a lot of you will be familiar with, which is internal time. I think that's probably the nicest name for it. It's also called the complete partial observable view or the correlation view. So this is Carlo Rovelli's view of time. It's also been, I think, developed more rigorously by Bianca Dietrich. The idea is that we don't have absolute duration, but we also don't have absolute succession, in the sense that we use an internal degree of freedom to parameterize change, and that internal degree of freedom is not guaranteed to be or to give us a monotonic parameterization. In fact, generically, it won't give us as monotonicity. So what's the situation? Well, classically, we have underdetermination problem, as we often find in physics, that we have different available metaphysics, different available ontologies, different available interpretations, however you want to spin it, that we can apply to the model in question. In this case, mini superspace models, which I'll say a bit about, or a lot about later. So mini superspace models classically are compatible with both relational time and the internal time view. However, and this is the really interesting thing, is when we have interpretational underdeterminations, it's very interesting when they give us different heuristics for developing the theory. In particular, the two interpretations motivate different quantization procedures. So for the relational time, the way I want to present it is, we call it a Schrödinger quantization, because it's modeled after the original Schrödinger quantization of classical mechanics. And I'll talk a lot about that later. And then if we follow the internal time view, the natural view on quantization is the more standard view about how to quantize these models, which is the Wheeler-DeWitt, leading to the Wheeler-DeWitt equation. So we have a classical model, we have two ways of viewing time in the model that are indistinguishable in terms of the observational content they imply the model will have, but they motivate different quantizations. And what's really interesting is that the quantizations lead to different quantum models with different properties. And I want to argue in favor of the relational time view and Schrödinger quantization on the basis that it has certain advantages related to how singularities are treated in the quantum model.
And of course, the question is, how should this equivalence principle and this identification be?
So we talk about singularity resolution. You see various discussions of this in the physics literature. I think it's one of the issues that in the philosophy literature is strangely not discussed in anything like as much detail as it should be. I think philosophically it's very, very interesting what we mean by resolving a classical singularity quantum mechanically. There's lots of very interesting work about what we mean by classical singularities. There's a very, very interesting discussion in the Stanford Encyclopedia article by Mercurial of this issue, but there is not much philosophical discussion, virtually no philosophical discussion, of the very interesting question of what we mean by resolving a classical singularity in the quantum model. What is a classical singularity? Well, here's a picture.
What I'm trying to say here is that
just like
if we find a method to start from a quantum gravity theory and
so in the kind of wild and crazy world of the full solution space of the Einstein field equations, there's lots of odd, interesting things. And the Stanford Encyclopedia article has a nice catalogue of different strange ways we can get singularities. But we're not in that kind of untamed territory. We're in the quite civilized territory of the cosmological models of the FLRW structure. And there's actually some very nice theorems about how these models generically contain a Big Bang singularity, so long as certain energy conditions are satisfied. And we can characterize the singularity in terms of incompleteness of causal path-directed curves and the existence of curvature pathology. So you have two kind of important aspects to what we mean by a singularity. We mean incompleteness of a curve, an observer traversing the curve will experience finite proper time. That seems pretty weird. Perhaps even weirder is the observer, there will be measuring devices they can carry, which the theory will tell us that the measurements will diverge due to these curves.
We don't know what exactly are the scales.
Generically, you can get one without the other.
And moreover,
which is actually quite odd. In this case, we have both.
And
I think, uncontroversially, we could take pathological behavior in an observable classical physical quantity to signal the breakdown of generalism. And so a requirement for something like quantum analysis. And our hope would be that this pathological behavior would resolve the pathological behavior would not be present in the quantum analysis. It's a reasonable hope.
Define also the geometry
So is there a quantum Big Bang, is there a quantum singularity, or do we find that there's some kind of resolution? Well, we've got to be careful. What do we mean by the singularity being resolved? And there's various proposals in the literature. And I'm not going to go into a detailed critical analysis of them. Really what I want to do is give you some, what I think are plausible things we'd like a criterion for quantum singularity resolution to satisfy, give you one example, and then move on. I'm very happy and I'm very interested to discuss other alternatives for singularity resolution and whether they would all apply to our model. So let's look at some, well, what I think are good requirements. First, we should be motivated in what we think singularity resolution is by how we understand the pathologies in the classical systems. And there should be some way of linking the two together, maybe in terms of a semi-classical analysis. First thing. Two, I think is very important, and I think some of the criteria which don't have this property have problems as a result of it, that the kind of criteria we use singularity resolution has to be at least in part dynamical. It can't be a purely kinematical criterion. And that those are the two kind of more physicsy motivations. Then from a more conceptual side of things, what I think we should do when we're talking about singularity resolution is make it as broad a notion as possible, so it doesn't depend upon how we approach either the problem of time or the measurement problem. So in that sense, I would like the notion of singularity resolution to be compatible with both the relational time view and the internal time view, and I'd also like it to be interpretation neutral. So by this I mean I don't think that the measurement problem isn't a problem. I think particularly for quantum cosmology it's a really severe problem. But what I would like to do is push an approach to quantum cosmology as far as possible without having to make a bet on which interpretation or none I'm happy with. So why the approach that I'm pursuing is not that we don't need an interpretation, but that we should resist having to take an interpretation as long as possible. So a simple criterion that meets all four requirements, in my view, is that the expectation values of all observable operators as evaluated on the generic state always remain finite. In particular, what we'd like is, if we have a classical quantity which is pathological, the corresponding expectation value should be finite. This seems to me a physically reasonable, plausible, and quite general criterion for singularity resolution, and that's the one I'm going to assume for the rest of the talk. Whenever I say singularity resolution, that's exactly what I'll do.
The blank scale, but they would vary.
So, interestingly, at least for some parameter choices, the Wheeler-DeWitt quantization doesn't lead to singularity resolution, in my sense. So, canonical quantization of mini superspace models leads to a quantum cosmological model described by a timeless Wheeler-DeWitt equation. Don't take my word for it, take Ashtokar's word for it. There's explicit calculation, which is really, really quite long, that you can show that for a simple parameter choice, and in particular for vanishing cosmological constant, the Wheeler-DeWitt mini superspace quantum cosmology has non-finite expectation values, quantities that are classically divergent. So according to this, my criteria, for these simple choices at least, probably more generically, the Wheeler-DeWitt quantization doesn't resolve the singularity. However, as I'm sure many of you know, there is an approach that follows broadly in the Wheeler-DeWitt quantization that does resolve singularity, and that is loop quantum cosmology. So in particular, Boswald and Ashtekar have shown this in different ways in different papers. In the context of loop quantum cosmology, the Big Bang singularity in mini superspace models is resolved based upon the introduction of fundamental discreteness. In particular, models that exhibit pathological behavior in the expectation values. Models that exhibit pathological behavior in expectation values of classically divergent quantities under the Wheeler-DeWitt treatment have finite expectation values under a loop quantum cosmology treatment. So if we think about it, we have classical treatment with pathologies, and some observable, the corresponding observable in the Wheeler-DeWitt treatment still behaving pathological, corresponding observable in the loop quantum cosmology treatment is not behaving, or the expectation value is not behaving pathological. So, in my sense, loop quantum cosmology satisfies the criteria for singularity resolution. And I'm not claiming that our approach does anything stronger or better than loop quantum cosmology here. Rather, I'm claiming that we can, using a different approach to the problem of time, but not using fundamental discreteness, recover singularity resolution of the same strength. So the standard canonical quantization leads to frozen formalism, perhaps misleadingly. The sense in which time has disappeared is perhaps not as severe as it's often made out. That understanding the wave function of the universe is certainly trapped in the energy eigenstate. It's not really that frozen because we can use this internal time interpretation, we can use deparameterizations to make sense of evolution and change in some sense in Wheeler-DeWitt cosmology and quantum cosmology. So I think calling it timeless quantum gravity is a misnomer. It's just that it doesn't have a rich notion of time corresponding to relational time, as I talked about it. But it has a robust sense of internal time. What Sean and I have done in a series of papers argue in favor of a different relational time interpretation of reparameterization of variant theories. And what we've proposed based on this different interpretation is a way to quantize in a different way, which we call relational quantization, and that leads to something with the same structure as a Schrödinger equation. And I'll talk a bit more about relational quantization very shortly. So what I wanted to do today, for the most part, though, after I kind of introduced the overall framework, is to talk about our results for a particular mini-superspace model, quantizing this model according to relational quantization, studying the solutions. And I want to emphasize that although our interpretational kind of route to this model is quite different, formally this isn't a model that originates with us, although we weren't aware of this paper till after we derived it. It predates the Walden-Unruh treatment, significantly predates ours. So they derived something with essentially the same Schrödinger equation in 1989 in the context of unimodular gravity. But they didn't pursue the analysis of the solutions to the equation in full detail, and they in particular didn't study anything like the bound scenario that we're studying. But so the model that I'm talking about is kind of philosophically based upon our approach. If you don't like our approach to the problem of time, you could if you liked, don't do this, but you could if you liked, think about the model as a unimodular gravity model and ignore the stuff that I've said about relational time. I think unimodular gravity and our approach to time are not unrelated, but certainly conceptually distinct. So what happens in this model, we get, as I've said already, singularity resolution, and I'll show this explicitly for some particular solutions, expectation values that remain finite into and out of the singular region, into and out of because we have a bounce, and we get some interesting novel features. Superpositions of values of the cosmological constant as per unimodular gravity, non-zero scattering length around the big bounce. So we have a deep quantum regime which has a very interesting structure. In particular, in this deep quantum regime, you find bound FMOD universe states that are the states corresponding to negative cosmological constants. And so this last feature is particularly odd and particularly interesting. And I'll talk about that in detail later as well. In essence, what we find is that the negative cosmological constant part of our solution has very, very closely related mathematical form to bound trimer states that you get in few-body quantum systems that are called FMOD states. And there's some quite interesting analogical reasoning that you can use, you can then employ based upon this correspondence between the FMOD states and our bound universe states. And I'll get into that at the end of the talk.
I would like to find this tensor, that is the effective metric at this level of description, such that the word lines of this particle.
So what is relational quantization? I'm going to be a little bit quick over this. we've written quite a lot about it already. Please refer to the papers if you want more detailed and kind
of course, to be able to read
thorough treatments of how our approach is where and how it departs from the standard analysis of constrained Hamiltonian systems a la Dirac, something we thought about a huge amount.
My region of interest with
so it's an alternative prescription for quantization of globally reparameterization invariant models. Globally. I'm not saying anything about systems which have local reparameterization invariant, i.e. refoliation invariance. I'm not at this stage claiming that our quantization procedure is applicable to theories which have local reparameterization invariance. In particular, everything I say is only going to apply to theories with a single Hamiltonian constraint. That said, it is plausible to think that this might apply to gravity, because at least in the shape dynamics formulation of gravity, there is only a single Hamiltonian constraint. So it is plausible to think about relational quantization in that context. In this approach, we end up with a Schrödinger equation, I've said several times. We've done this perhaps too many times. So if you look, the original treatment we did was using a path integral method due to Fadiev and Popov. We then have a quite long paper embedding it in the Dirac quantization constraint Hamiltonian methods. And more recently, and I think perhaps more intuitively, compellingly, we've done an analysis in terms of Hamilton-Jacobi theory, which I'll talk a little bit about here.
Change the scale over which I have done the approach.
So one thing to make clear, in our view, time is not a physical observable. However, in quantization, we should retain a monotonic parameter that orders variation and correlation between
and replace it by something much simpler.
I'll give more details about that later. So we retain time in some sense, but we don't introduce time as an observable.
Which I'm going to consider as an extended object.
But we do, what we want to say is that really what's physically real is variation and correlations between all the operators.
The center of mass word line I will use to define what is the metric that I'll state.
I'll talk about that in a second.
And
so the approach is based upon an ambiguity, a quite subtle ambiguity, that for theories invariant under global reparameterization, there's a variable that's canonically conjugate to the arbitrary parameter associated with the Hamilton flow of the Hamiltonian vector field in phase space. So we take the phase space of a reparameterization invariant theory, the Hamiltonian generates a flow on the space, it's actually a null flow, and that flow we can arbitrarily parameterize, and there's some variable that's canonically conjugate to the parameter of that flow. And for globally reparameterization invariant theories, this is the Hamiltonian constraint itself, and this implies that the relevant conjugate variable is a constant. The question is then, how should we interpret the constant? So to give you some context, for a simple particle model, this constant is energy. For the mini-superspace model, this constant is cosmological constant. So the question is, how do we interpret the conditions on this constant that are enforced by reparameterization invariance? So one option is to interpret it as constant of motion, the value of which is determined by initial conditions. This is our option, this is a less conventional option. The more conventional option is to take it as a constant of nature that takes certain values fundamentally. And as I hope you can see, the big difference is when you go to a quantum treatment, we don't take superpositions of values of fundamental constants of nature, we do take superpositions of values of constant of motion. So although this ambiguity doesn't make that much difference classically, in the quantum treatment it's going to make a huge difference.
Center of mass, and obtain the word line, and then define the center of mass word line in any other frame by simply the transformation.
I'm going to go back to it in one more slide, so I'll ask you again in a second.
The problem now is to generalize that idea.
So the idea is that if you take constant motion interpretation, so we treat, just in a simple particle model, let's say, we treat energy as a constant of motion, then we use the standard Hamilton-Jacobi formalism.
The idea first is that I need to define the
given we have this, we can do a separation. Ants does for.
Okay, so how do I define the rest frame of the collection of particles? First, I take an arbitrary point. I assume that this is the rest frame of the collection of particles.
So we can do the separation answers, and they have a reduced equation just for the W.
Space-like
and so in the end, the idea is that
this one is generated by
the constant of motion interpretation, treating energy as a constant of motion,
the intersection
allows
of my
you,
word lines
gives you
a
basis for using the full Hamilton-Jacobi equation, and treating energy as a constant of nature forces you to the reduced equation,
the total momenta
which
of this.
You have to take my word for it, but it's true. In the end, you can actually rebuild the same set of solutions from either equation.
That momentum will not in general be in the same direction as I'm moving, but then I look at this as a map from some four
if we take the
vectors,
constant of motion interpretation, we have this equation, take the constant of nature interpretation, this equation, under the constant of nature interpretation, the reduced equation is the only thing we have, but we can rebuild the dynamics using the partial and complete observables program. In fact, to give you a look, for people who've looked at the partial and complete observables program and found it a little bit hard to get into, in fact, in the Hamilton-Jacobi formalism, everything's incredibly simple, because the expansion equations that Dietrich and Ravelli used to actually write the observable flows are actually the integrals of motion from the Hamilton-Jacobi. Something we go through in one of our papers quite carefully. So the idea, once you're in Hamilton-Jacobi theory, if you take the constant of nature approach, you use the reduced equation, you use the partial and complete observable schema, you can rebuild the full set of observables, albeit without having a monotonic parameterization. And in this approach, the relative values of physical variables are only ordered relative to an internal clock. It doesn't have to monotonically increase.
But here things are easier, are manageable.
Is that okay?
Okay, so
do you want to come back?
This way you produce a field that defines for you the rest frame.
So classically, the idea is that these are physically indistinguishable.
The observer at each point.
So we're not claiming that the internal time Ravelli type view is deficient classically in terms of anything observational or any structure that we've got rid of that is going to prevent us from describing the world classically. What we are saying is that
I'm looking for a correction to the center of mass.
Taking the internal time view, in a sense, removes some structure that's useful or important for retaining description of time.
Start from this point.
It's relevant for how we think about the quantum theory. So the motivation that we get from starting with the reduced equation, as opposed to starting with the full Hamilton-Jacobi equation, how we treat quantum theory is entirely different. And you can actually see this really, really simply if you actually look at Schrödinger's original derivation of his equation based upon the Hamilton-Jacobi equation. So if you just apply the same kind of heuristic argument towards the quantum theory that Schrödinger did for the full Hamilton-Jacobi theory of Newtonian mechanics, if you apply it to the full Hamilton-Jacobi theory in our case, you end up with a Schrödinger equation. If you apply it to the reduced equation, you end up with a Wheeler-DeWitt equation.
Basically by summing up the position of the vector.
So in the end, if you take one interpretation of the constant, you get one root quantization. If you take another,
and exponentiating back. So that would give us, in some sense, an average. Weighted average of the position of these particles. And
the interesting question is then
the correction of the center of mass. If I assume that I start.
What happens if we take the route that I'm
But of course,
advocating?
that recipe depends on
agree or
which
disagree with my motivation. If the route that I'm advocating leads to a model that can make predictions that the other route can't, then that's something significant, irrespective of, I think, irrespective of whether you believe the motivation. So I'm not going to say now that we have novel predictions, but we certainly have structure which indicates that our modelling framework is not going to be observationally identical to the
points that are on the center of mass word line, and Beagle has shown that this recipe.
So I'm going to talk a little bit about the mini superspace model and
which is
the sense that the mass will get a little bit
underlying
involved, but don't
However,
kind
we feel that
of
this
worry.
is the natural
Like I'll also illustrate things with diagrams and give you a bit more of a
of the space-time that you
explanation of what's going
obtain by
on. So where do we start? We start with a very, very simple cosmological model. So homogeneous, isotropic, spatially flat. The massive content is a massless free scalar field. So you're not really going to make things much simpler than that. Even though it's so simple, it still becomes complicated. So what do we have left? We only have the scale factor and the scalar field. So we have geometric degree of freedom and a matter degree of freedom. What we can do is actually follow through from the Lagrangian treatment from the Einstein-Hilbert action, which I've been told we should in fact call the Einstein action, so maybe I'll start. The Einstein action, scratch that out. We can derive it, we can follow the ADM procedure, and which probably should be called the Dirac procedure, and derive a constrained Hamiltonian theory. So where we've introduced conjugate momenta to both our variables, and we have a lapse multiplier, and lambda
as the object's kinetic energy changes from 0 to some large value, the effective curvature that you measure.
Of course, this is a coordinate-dependent expression, and we want to talk about singularities, so we'd actually quite like to have a coordinate-independent way of writing the Hamiltonian, so we can talk about the configuration space and the dynamics without reference to particular set of coordinates, which will enable us to show that the singularities we run into aren't an artifact of a bad coordinate choice. So what Sean has done is written this Hamiltonian in a coordinate invariant way, introducing this metric which we can identify as the Bossey metric. But we can just, in a sense, a particular choice is given by fixing this metric, and we transform between these two representations. The idea is that we now can use a variety of different coordinate representations, or the coordinate-free way of writing things, to express our model in different ways. This is particularly helpful for solving the equations and setting up initial conditions. The solutions are geodesics of the metric, and we get two constants, one corresponding to the scalar field momentum. The scalar field doesn't play that much of a dynamical role because we've made it quite simple. And the second constant, which we're taking, is a constant of motion, as per earlier part of my talk, which is the cosmological. So there's a boundary. So in the coordinate choice that we started with, you can think about it as a result of A being constrained to be A positive. So this corresponds to introducing a boundary configuration space, and at the boundary we can show, in a coordinate invariant way, that space-time geodesics terminate with finite proper time, and there's a curvature pathology. And although in fact our model is not within the conditions of the Hawking-Penrose singularity theorem because it violates the energy conditions, as almost identical logic to the singularity theorems can be applied to show that the singularities in both these senses do occur. And so to give you a bit of a we've chosen a parameter of normalization such that the singular time is -1. This would be the two branches of the solution.
Yeah, so
you think about
if you can go to the slide where you talked about the different regimes, I just have first a clarification.
A crunch scenario.
What is the difference between regime
usually maybe
2
we just
and
cut,
regime 3?
ignore one branch of the solution and think about this as our Friedman universe.
Regime 2, we imagine the regime in which you are
so
trying to consider an object of this
one branch in particular,
extension,
branch here,
and
within
the
time,
object, space-time varies
volume
rapidly.
goes to 0.
So that's a regime in which,
What's
for
the
instance,
field doing?
in this graph, in this
Blowing
picture
up
that
to
they
-infinity.
have, you are trying to
So you can see why
probe
this is going to be
space-time with an object of this size.
Feature in the model because we're condensing the scalar field down into a tiny.
On the other hand, you could try to probe
in
space-time with something of this size.
volume.
Then you would be in regime number 3.
So
because over this region, the space-time is.
This is the classical model.
But
We'll
the
come back
variations, the
to these
curvature are very
classical
small.
solutions.
Okay, so in that case, what is the
limit
difference
in
in
which
regime 3 and
they
regime
get
4?
recovered?
regime
But
4
to
is
give you
already
a
classical.
kind of
Regime
foreshadowing,
4 is the
the
classical
idea is
regime
that
where
for
you
our
describe
model,
particles in terms of point-like
this
objects
area
moving
here
on a given geometry.
So regime 3 and regime 4 is only the differences in the matter side? Because on the background,
change from 3 to 4.
But in between, there'll be
from
quantum
semi-classical,
regions, things go.
Matter is described quantum mechanically here. Here, matter is described already classical.
So only on the matter side, right?
Right.
Okay.
Yeah, we left the full quantum regime unexplored.
So,
from our point
in the
of view,
quantum
we are
theory,
very
the
agnostic
existence
about
of the
what is
classically
quantum
singular
gravity.
boundary leads to difficulties in finding
The only point we make about
representations of
quantum
symmetric
regime is
operators
that
in
it
Hilbert space.
should have the property
Specifically, the presence of a boundary allows the possibility of boundary terms to contribute to the action of the adjoint, and self-adjointness requires that the boundary terms vanish. So we can kind of slightly heuristically think about
I very much like this idea that one should worry about how matter couples to
where we
gravity
get some kind of extra
quantum gravity.
boundary
This is
term.
very much why
A less intuitive way of thinking about
that's very nice.
this problem is according to the
but you seem to still hold on to some properties
theory
of matter, like center of mass,
extensions, which you can classify operators into three.
If you are going to be radical
classes,
about the space-time picture,
operators
that
that are
emergent,
essentially self-adjoint,
couldn't one think that
operators
in
that
regime
are,
3 particularly,
not self-adjoint,
you have
self-adjoint
some notions of
extensions,
expectation
and operators
values
that are
of
not
your
that
stress
are,
energy tensor like you were doing, but not any corresponding
they're not
definitions
self-adjoint,
for
and
center of
no
mass.
self-adjoint
No,
extensions.
I agree 100%.
And so the correspondence between these and this way of thinking about it in terms of boundary terms
question is, how do you go from that regime to regime 4? Then presumably you want to take this
category
region
where
which you have
the operator
value
is
of
essentially
the
self-adjoint
tensor
is one where the square integrability
and say
conditions
that
of
somehow is a
the
particle.
vectors in the Hilbert space
And now
are
you
strong
want to
enough to
convert that
guarantee the
into a
boundary
word
term
line.
disappears.
The only idea that is
the-
natural is this, I mean, people can invent that idea.
case where we
But
have
the most
self-adjoint
natural thing would
extensions
be a covariant notion.
is where we can have actually families of boundary conditions.
So
which
we think that that's
we extend the operator, we
And
add
then
in
once you
families,
have these word
the
lines,
domain of
say,
the
okay,
operator, we add in
these are the
families of
word
boundary
lines of these
conditions,
free particles.
and this ends
what
up
is the space line?
giving
What
us
is the
conditions to kill the boundary
Yeah,
term.
just the point is,
And the
shouldn't it
problematic
depend more on the
case
states
where we
you
have no
choose,
self-adjoint
to do this
extensions
averaging
is
of
where
stress
there
and
isn't
tensor? I don't see where that information is going in.
killing
Oh
us,
no,
it's
of course.
always gonna come back.
What you imagine is that
So
you
there's
have
a quite complicated
another
literature
regime
on
which you have
how we should understand the
space-time
behavior
and
of
a
these
quantum
boundary
theory
terms or
in a
boundary
given
forms
state.
with the von
So,
Neumann theorem.
in that given state, there
theorems.
would be an
I can
expectation
give some
value of
references
energy
for that if you're interested.
And for that given
but the
state,
two
you'd say,
pictures
well,
are
this state corresponds to particles
consistent with each
moving
other.
with this.
And so the thing that's
But what are
very
the
odd
properties of the states?
No.
is that
Well, you use
the geometric degree of freedom,
the particular
i.e.
state you want
A,
to study. So,
Right.
so somebody tells you, well, here I
it
have
has
a
a
quantum
particular
gravity or
boundary
a
term,
semi-classical description
and
of the universe. So, and
sorry.
here is the state of
the
the
momentum
universe.
associated
Okay,
with
how does
A
that
has a particular
look?
boundary term,
If I want to describe it classically,
and
so they
this
were given
transforms
these things-
differently
these
to the
things were
square
given to you in
integrability
regime.
conditions.
Both the space-time
So it
was
means
given
that
to you, and
very
the
oddly
state of
the
matter fields were given to you. And now
standard
you're supposed
canonical
to read from
quantization
that
procedure leads
what is
to
the
an
description
algebra of
that-
self-adjoint
that
operators
is the recipe.
in some charts but
process
not in
of
others.
Okay, let's talk later. Thank you.
So in particular, in the chart which we started off with, where with A and phi, you can show that the operator is not just essentially self-adjoint, it actually fails, there's no self-adjoint extensions for this operator. And this is actually a fancy way of talking about quite a familiar problem, that there's no momentum operator for quantum theory on R+, which has been studied by Isham and by various people. Interestingly, and this is something that confused us a little bit, one would take this as an odd thing in the context of the Stone-von Neumann theorem, since we expect for finite dimensional systems unitarily equivalent representations. And the small detail which I was unaware of, but is apparently obvious to experts, is that the Stone-von Neumann theorem actually requires the phase space to be R2n. So because our phase spaces you can think about it as the cotangent bundle to R plus R, the theorem just doesn't apply in this case anymore. So the Stone-von Neumann theorem is not, in fact, a theorem that applies to finite dimensional systems. Finite dimensional systems where we can specify the phase space like that. So that's an interesting and I think important point that maybe isn't as familiar as it should be. So how do we get out of this problem? We find a particular chart where there is a momentum operator. In particular, we use a conformally complete chart where we in a sense, map the boundary to infinity by taking this variable change where we've introduced
That's your preference.
So mu is log v, and v is just
one state that is more localized, and from that you try to read
volume variable. So this corresponds to taking form completion, and in that chart we actually have the momentum operator is essentially self-adjoint. I have 5 minutes left in total. Okay. Can I run 5 minutes over?
But my point is that even
as always, you'll miss the videos.
Even if you do that,
okay, so
even if you
that sets up the model. What's the structure of the model? What features does it have? And obviously the important thing is, are the expectation values finite? Immediately we would expect the expectation values have to be finite, just from the generalized Ehrenfest theorem. And so long as the Hamiltonian is self-adjoint, i.e. so long as we have unitary time evolution. So we can apply relational quantization as per the description I talked about.
Thank you.
Do a separation ansatz, so we separated out the time evolution, and then try and solve the eigenvalue equation for the Hamiltonian operator. And the important point is that this operator, for us to have singularity avoidance, it has to be self-adjoint. So we can write it in 1 loop 3 form in terms of this Dillon-Bershon.
My question is, if you're thinking of actual test bodies, they're probably...
In fact, even this eigenvalue equation we can separate again. The V, i.e. volume-dependent part, is where a lot of the interesting physics is. So we do another separation ansatz just for the V part, because the phi part satisfies a wave equation. And so we end up with a Bessel equation. So, and what we want to do is make this, find or make sure that the operator for to guarantee the overall Hamiltonian self-adjoint, we have to make sure that the solutions to this operator have the right relationships with it, i.e. the members of the adjoint and the domain of the adjoint and the domain of the operator. And we need to apply the theory of self-adjoint extensions. So the really interesting thing is that the way that we do this depends upon the sign of the cosmological constant. For negative cosmological constant states, we get one family of solutions, and for positive cosmological constants, we get another. So when the cosmological constant is negative, we get Bessel functions of the second kind. A set of bound eigenstates belong to self-adjoint. The operator is labeled by a discrete set of extension parameters. So this procedure of fixing our operator to make it self-adjoint introduces a dimensional parameter. And fascinatingly, the equations describing these bound states are almost identical to those used to describe this F-mob effect, as I mentioned earlier. So what is the F-mob effect? In the limit where 3 identical bosons are governed by an effective one over R squared potential, where R is this term dependent upon the binary interaction, oddly, it was predicted in the 60s and confirmed in, I think, 5 or 6 years ago. You get these stable bound trimer states that are called F-mob states, which in some sense, for those of you like topology, the analog of the Bormian rings. If you cut one, they all fall apart. So the bound F-mob states form a geometric series with a spectrum dependent upon the self-adjoint extension parameter. And what's interesting is we think about this, the F-mob effect as a universal phenomena described by an effective field theory, with the extension parameters fixed by the underlying physics. So in the end, we're describing this funny bound state of three bosons by an effective Schrödinger equation with a 1 over R squared potential. And the extension parameter that shows up tells us about the limit in which this effective model breaks down. So it's actually quite interesting that the structure of our negative cosmological constant part of our wave function have a similar structure to this, because it actually suggests that there's a dimensional parameter coming into the theory, and we can treat the quantized cosmological model as some form of effective field theory or effective model. So I think this is very interesting, and potentially a way in which we can think about the F-mob experiments they do as analog models for our cosmological model. Okay, I better speed up. So the positive cosmological constant solutions are a different form of Bessel functions. They're unbound, and they have a particular behavior that, again, depends on the self-joint extension point that shows up. To give you some idea of what they look like, I'll show you first in a limit where we can neglect the scalar field, which is something like a de Sitter limit. This works. So this is the wave function amplitude. You see phi is kind of switched off. And you have this kind of quantum region here, and it'll bounce away. So these have been set up in initial Gaussian states. So it's actually more instructive to see the two-dimensional picture where this is the expectation value. We get the bounce in A. So looking at the expectation values on their own, if you look at the volume expectation value where red is the classical value, we see at late times the two coincide, semi-classical limit of our model. These are the unbound states, right? So the semi-classical model limit of the unbound states matches the classical model, matches the Friedmann universe. But in this quantum period, the expectation value wanders away from the classical value, but it remains finite. And similarly for the scalar field. This is, in a sense, the only thing, or the most important picture in the whole talk. This is what we want to say is physically real. The successive values of this parameter here, t, we're not taking as a physical observable. What we want to say is physical is the successive values of the correlations between the expectation values. So we need the parameterization gives us an ordering, but this, if we think about different like a reparameterization, we don't want to think about this changing that. So the kind of physically meaningful structure is not dependent upon the parameterization. It's ordered succession of correlations between the expectation values of both the dynamical degrees of freedom. Whereas in the Wheeler-DeWitt picture, one of these would be kept as a classical value and used as a clock to parameterize the other. And so you wouldn't treat them both as quantum. And there looks like perhaps some kind of an inflationary period in this region here, something we'll investigate. Okay, I'm almost finished. So we can look at the full video of the full wave function. Has quite complex structure around the big bounce. In fact, you find that the wave function, or the expectation value, it's not that the wave function is spread like a Gaussian around the expectation value in the quantum period. It is in later periods. So things get very odd, and there's these interesting interference between the ingoing and the outgoing modes. There's a lot of structure in the actual wave function. So we can write the general solution. So far I've just been talking, those pictures and those videos were all of the unbound part of the solution. The general solution contains bound and unbound parts. So we can actually think about use the analog model to think about how the solution fluctuates. We can think about it in terms of a scattering experiment, with the unbound wave function scattering off the bound wave function around the origin. And then we can interpret the dimensional parameter that's in the context of the unbound part of the wave function as a phase shift that picks up through the scattering. And the interesting sense is that the actual experiment that they do on the FMOV states is to scatter light off the bound states, and they observe a phase shift with the similar character to what we're talking about. So the idea would be that to try and use our model to set up something like an analog experiment to kind of get new ideas and maybe even new features that we can explore. Really, if we wanted to do real physics with this, the model isn't rich enough. If we wanted to try and observe this phase shift or make predictions from it, we probably need to move beyond mini superspace. What we're thinking about doing is maybe looking into Bianchi models. Thank you very much.
each time about what's going on. So by looking at like the observable A and tracking whether that goes to 0, is this right? I mean, you're really only looking at whether the spatial curvature is smoothed out, but right? But one could also have space-time curvatures, which would be measured if one had time by something like the time derivative of A, or the Hubble parameter, something like that. I think.
Yeah.
So if you had time in here, it would just ask, well, what happens to dA by dt? But I guess it's also further complicated. I don't know exactly how one would pose that question in the relative time framework.
So
okay, does that make sense?
Yeah. So I think we don't have time in the sense that we don't want to identify it as an observable, but the mathematical quantity dA by dt is well defined in our framework, and it is finite. Does that help? So we in the end, if we can write down dA, we can calculate dA by dt and say this thing is finite, but because we don't want to identify duration as physically meaningful, we wouldn't want to say that quantity perhaps is if it were to be kind of instantiated in the world, what it would mean. So I guess the more interesting issue would be is if we had more geometrical degrees of freedom, and so it wasn't just spatial curvature that we're modeling, exploring how they behave. That would perhaps be something we can do in the more complicated models.
Thanks.
So, just when you say you have this relational succession of these fields, how do you exactly derive duration from it? I mean, duration is in the space-time would be the lapse, right? For example, that reads off what the duration is. How do you construct the lapse explicitly from a history of relational?
You mean in the quantum theory?
Or even if you have a classical history of these two.
Oh, so in the classical theory, you can basically, this is formula in the Barber's treatment for how you can basically write down a metric, derive a metric from the lapse and I think it's square root t over e minus v or something like that in the particle model. I'm sure you could do something similar here.
You mean in Berlin-Schacht-Wheeler?
No, just in the paper with Brendan Foster, there's a definition of duration in based upon the lapse and the Hamiltonian constraint. So the point is, for any given parameterization, you're specifying a notion of duration and you're fixing a lapse function, right? And the idea is that the theory is invariant under transforming between them. But in this kind of Machian sense, there's a natural, emergent duration measure that you can derive based upon the constraint. That's actually, sorry, I'm talking rubbish. That's lapse invariant, and then that ends up being in the particle model equivalent to Newtonian time. But the level of the classical model, I don't think the approach that we're taking is in any way different from Julian's. Certainly the way that we're interpreting the constraint surface is different, but the way that we think about duration, the reconstruction of it would be identical.
Just comment on one thing that we discussed earlier, and I'm not sure if it's a problem or not. I think probably it is not. Just because I was saying it earlier and Chris was there, so I think I should just say one thing is that what worries me a little bit is this use of coordinate transformations and different notions of momenta that you get so that you require a self-adjoint extension. It's just, I would expect when you write something in terms of this geometry of this mini superspace, things would be, in a sense, coordinate invariant.
Sure.
But maybe it's not, maybe the quantum machine.
So I think the actually really important point that I think I missed in our discussion this morning was that, and this is the thing that confused us for a long time, is that the momentum operator is, so there are coordinate invariant operators, but they play, the operator that you single out as the momentum is different in different charts. So the problematic momentum operator has you can represent in all charts. So in all charts, there's a momentum operator. There is a particular operator which in all charts fails to be self-adjoint. That operator only generates shifts, it only acts as a momentum operator in certain charts. The point, by using the conformally complete chart, the idea is that the operator that plays the role of momentum in that chart is self-adjoint. So that operator is well-defined in all charts. The problematic operator is well-defined in all charts. So it's not really about using a privileged chart, it's about using a particular momentum operator which, in a given chart, acts as a momentum operator.
So I have many questions, but because of time, let me ask you much relevant one, which is in your calculations, you have to have a cosmological concept, which is not necessary for me.
Sure.
So this is more specific than that, let's say, how singularity is resolved into cosmological.
Sure.
And the second question is, if you cannot have local reparameterizations, then you cannot include things like inhomogeneities in your universe, right? Like this, even prohibited inhomogeneities, which you know are true from mechanics and classical.
Well, the basic Bianchi models have a small amount of inhomogeneity without. Sorry, you're right.
So for inhomogeneities, you need to require some sort of global reparameterization, which if you don't have, you cannot have. Is that right?
So this is where we kind of pivot to shape dynamics. So if we reformulate things in shape dynamics, then we've exchanged the symmetry, so we have this conformal symmetry, and we don't have local reparameterization invariance. We have a third foliation up to reparameterization, and then we can start talking more meaningfully about applying relational quantization. So I admit that, like, without this move to shape dynamics, our approach is severely restricted, but with it, it isn't entirely, like, the path isn't completely blocked. So on the first point, so this actually is quite an interesting turn of fate, I suppose, that in fact the lambda equals 0 part of our solution space is not actually particularly well defined. It doesn't connect with the other parts of the solution space. So it's just a real shame that Unruh and Wall didn't finish their calculation, because they could have actually used it as a basis to predict the and we only have semi-classical limit for the positive cosmological constant. So if in 1989 they'd studied the solution more fully, they might have been able to use this model as a basis to predict that the cosmological constant has to be positive and non-zero. Now, like many years after the fact, it's a bit cheeky of me to claim this as a prediction, but maybe I will.
So just to go back to the shape dynamics one, then if you take that one of view that you go to shape dynamics and then use this quantization scheme, then you also require some sort of conditions coming from this symmetry breaking where you go from shape dynamics to GR.
Sure.
So then your quantization scheme has to respect this.
Of course. So we'd have to fix, obviously Enrique knows a lot more about this than me, but we'd have to restrict from the sector that's globally hyperbolic to the sector that's CMC sliceable.
It should just like a non-trivial condition.
Of course.
So your notion of similarities was that you have a similarity whenever expectation values of certain observables are infinite or diverge?
So we did it the other way around, in fact. Our notion was that singularity resolution is when classically divergent, or classically pathological or divergent observables have finite expectation values for all times evaluated on generic state in the quantum theory.
The classical part is also important. If it's classically divergent.
Yeah.
Because it seems a bit strange to me why should worry about classical quantities, whatever they do.
Well,
For example, classically you have singularities whenever your equation of motion is very bad, right? Time evolution somehow stops at certain points or at certain places. Or at certain places.
sure.
In your case, I would say, okay, the Schrödinger evolution is well defined and the way things can evolve to arbitrary times.
Yeah.
There seems to be no singularity.
Sure. So I think there's an interesting.
It would be requiring less than what
Sure.
we're doing now.
So there's an interesting relationship between the sense in which you want to treat quantization as a means for resolving the singularities in the particular form of space-time singularities that you find in GR models. And I think an equally interesting question about when and how and why we should think about quantization as dealing with singularities that you find just in normal classical mechanics, like the Norton's dome or various of the examples. And so it's not something I've looked at carefully, and interestingly is actually related to the question of self-adjointness as well. So there's a wonderful paper, which is typically John Ehrman, that's extremely complicated and long, where he looks at how and when we should think about these classical singularities in terms of the trajectory stopping, how we should treat them, and whether we can fix them in quantum mechanics. So I think this is a really interesting point, but it's not something I've thought about that much.
Please, do we have time? Yes, we have. So I wanted to address this question again, the reparameterization problem.
Sure.
Following up on discussion. Could you go back to equation number 4 in your presentation? That's where you write down. And I may have misunderstood what you were doing earlier. I'd like to try to clarify here. So you are, in fact, you've rewritten this in terms of new variables. And in which case, you have an independent term, which is what you call random term. That's a later equation.
That's a later equation.
But you are indeed still required.
Yeah, just speak a little louder.
Yeah, I'm sorry. Yeah, you are indeed still requiring, as I understand it now, that this capital H does vanish. Is that correct?
Well,
now you're giving a new interpretation to the cosmological constant.
Yeah.
Now as becoming an argument.
Yeah.
So in that sense, it looks as though you are indeed you have retained the same classical dynamics in the quantum theory. So that was a reservation that I had about your approach. And it looks as though what you've done is that you've simply chosen made a particular gauge choice for the lapse time. So I would interpret the time which you are using, which you say is a non-observable parameter, as actually a particular choice for time, which could
Sure.
be measurable within this month. But maybe this is something that
Sure. I think there's a tension. Actually, Nick brought this up based on the discussion of the last talk. There's a tension between we're treading a very, very fine line between trying to keep this middle position where we don't have duration but we do have succession in the quantum theory and falling back into the Newtonian time interpretation. But I think it's still true that if we take the fundamental representation of our physics in terms of these correlations between expectation values, correlations between operators, we don't have a privileged notion of duration in the model. But we certainly have formal structure, which I think maybe the point would be that our quantum model might be interpreted in terms of Newtonian time, which I guess is also exactly what Unruh and Wald did in their original paper. But we don't think that's a necessary interpretation. So there is another issue which is rather complicated, that the way that the lapse multiplier has been, or at least the normalization of the Hamiltonian has been fixed, seems to privilege a particular vacuum state. And I'm not sure whether that's necessarily a fault or a feature, because things like the under effect do seem to tell us maybe there is a sense in which we want to privilege a vacuum state. So I think there's definitely a kind of a nuance in how you treat time in our model the other way, if you want to think that maybe we've reintroduced duration.
Follow-up?
Thank you.
Just a quick comment regarding your notion that the approach is in some sense insensitive to the interpretation. And I think I want to challenge that in the sense that you are somehow giving preferential treatment to expectation values in contrast to, let's say, eigenvalues, or you're discarding this kind of approach, which people think of branches of the wave function, sort of things of that sort. So what you have done is in some sense tied to a particular interpretation and will not could not be viewed as resolving singularity if one decides to take interpretation of view that says sticks to eigenvalues. Very interesting question.
Thanks. That's a good point. So I think maybe satisfaction of all my 4 desired properties simultaneously might be difficult. But at least these were the norms that we were trying to work by. I guess the point would be that to the extent to which you really want to recover like semi-classicality, the expectation value is very useful. But like, I think you're right, maybe they do at least like implicitly make what you're doing sound a lot less like an Everett interpretation. So I accept that. But personally, I am not tied to this notion of singularity avoidance at the cost of anything. I think this is a useful one. I see interpretations as tools to get interesting heuristics for developing models and getting prediction out of models. If someone tells me, no, if you interpret your model according to the Everett interpretation, then you'll get all these interesting features, I'd say great. Personally, I've got a lot of doubts about the Everett interpretation, but if someone can show me something cool I can do with the Everett interpretation of our model that I can't do otherwise, I'm perfectly fine with that.
So your recipe of quantization, suppose you apply it to the relativistic parameterized particle. The usual quantization you get Planck-Gordon integration, right? Because in your case you don't.
So I actually can't. We've had this discussion 2 or 3 times, and I know that we've done the Sean work through the model, and it is non-trivial how you can recover the right dynamics from our approach. But I can't remember what the detail is, so I'd have to ask Sean and get back to you. But we've had that. I think Bianca Dietrich asked the same question. I remember we had an answer, but I don't remember what it was.
There wasn't anybody else. How hard if you have sort of superspace or mini superspace kind of framework that you're working in, something like this kind of thing, how hard is it to actually come up with bounces, singularity avoidances and bounces? And I feel I've seen in sort of other cases where people have done similar sorts of approaches.
Sure.
Recently, there's sort of ones based on Hamiltonians you would expect from string theory that have the same kind. Do you have a sense of how generic this sort of bounce behavior and singularity avoidance is? Is this kind of fairly unique, or is this fairly generic?
So I think it's a really good question. I think there's a few different things to say. So the different bounce scenarios are not identical. They seem to have different features. There's a model by Turek, which is quite interesting as well. They have some things in common, there's some things different. Within the kind of canonical mini-superspace approach, I know that besides the loopy approach, or the loop quantum cosmology approach, there's also you can use particular types of dust field that violate the strong energy conditions that will give you a bounce as well. So certainly, I'm not saying that there's no Wheeler-DeWitt type model that doesn't have something like a bounce phenomenology. But the important thing to remember is that if you are in one of these bouncing Wheeler-DeWitt models with this some kind of like dust field that I think it's like pressurized fluid or something like that, you're going to get quite different physics, because although you have a bounce, you still have a single value of the cosmological constant. So the features of our model, I think, are going to be particular to models where you have superpositions of the cosmological constant, because it introduces quite different physics.
Okay, the next question. Okay, brief question.
Is that, so it seems that there are so many ways you can have a bounce in singularity resolution in these kind of models, and this for like all these models. Because they are finite dimensional form of the candidate, these are very simplified functions of gravity. But to take any of these approaches seriously on cosmology, one should go beyond such simple setups and see whether this kind of singularity resolution is still valid or not.
Sure.
And so for in this particular case, for example, I would think that the difficult task would be to apply this to shape dynamics and see whether it can take that correct. So maybe that's one of the reasons why bounce was in their resolution is not generic, but it's much more easy to get in mixed super space cases. But it's they're from beyond bounces and so on, all sorts of stuff, even from string. But it's much more difficult to derive this from a more quantum theory of gravity as opposed to a quantization of a classical resource.
Completely agree.